Hi guys, in this video we're going to discuss all the problems from the Codeforces round 142, the educational Codeforces round 142 that was rated for Dev 2. So we'll start with we'll be discussing the A, B, C and D problem, not the E, F1, F2 problem. I'll have to see them myself actually first. So cool. Let's start with the problem A. The problem A name is Gaming Forces. The problem states that Monocarp is playing a computer game. He's going to kill n monsters. The ith of them has a health HI. So then he has two spells and he can use any one of them. So in one of these operations he can actually choose two alive monsters and decrease their health by one. In the other kind of operation, what he can do is that he can choose a monster and can kill it, and a monster dies when his power exactly becomes zero, right? So then they have given us the constraints about the number of test cases, the number of monsters and the health of the monsters. So not that useful because they are actually pretty lenient, but it's not required. Anyway, it's going to be a order of one solution after we take the inputs. Yeah. So what there's a simple observation over here that it would only make sense to perform the operation 1 if you are having two monsters with power 1, right? So if any of the monsters has a power greater than 1, then it actually doesn't make sense, because if let's say there are two monsters with power 2 and 1, in individually you can apply the second kind of operations, and in two operations you can beat them. uh, it it would only make sense to apply the operation number 1 when you have two monsters with powers exactly equal to 1, right? So if you have two monsters, let's say with power 1 and 1, then you can actually apply the operation 1 only once and you can kill both of them. So yeah, that's it for the solution. This wasn't a tough thing, I guess. Yeah. So what I have to do is that I'll simply have to count that how many number of ones are there. I'll store it in my count variable. So once I've done that, the answer would simply be n minus count divided by 2, because let's say I had four monsters with a power 1, right? Then I can perform two operations. In each of those two operations I can select two monsters, and in this way I'll be able to kill all the four monsters, right? So it's basic. So half of the monsters with the power I would actually die without incurring any cost. I hope that makes sense. So that's what I'm doing exactly over here. Cool. This was a simple one. I'll proceed further to B. So B question isn't tough, but it had you can say a edge case, which actually even took me a lot of time to figure out, and I had actually done two wrong answers by the time. So it states that Eve is a beginner stand-up comedian. Her first show gathered a grand total of two specters, Alice and Bob. Cool. So Eve prepared A1 plus A2 plus A3 plus A4 jokes to tell. So basically these are types of jokes. So there's type 1, type 2, type 3 and type 4. So the type 1 joke is actually preferred by both Eve and Alice and Bob. The type 2 joke is liked by Alice but is not liked by Bob. The type 3 is liked by Bob but not by Alice, and type 4 is liked by neither of them. Then initially both the specters have their mood equal to 0, right? And when they hear a joke that they like, so their happiness or their mood increases by 1. When they hear a joke that they don't like, their happiness or mood decreases by 1, right? So as soon as someone's mood becomes negative, then he gets up and go and the show ends over there itself. Else, when the total number of jokes are over, then the show would end. So we have to tell that till what time the show would end, or we can say how many jokes can actually be delivered in that particular show. So that's the problem. Let's talk about the solution. So initially I've stored so this is the type 1, type 2, type 3, type 4. I've stored them in A, B, C, D. Then I've taken two variables, Alice and Bob. So this actually would represent the happiness of Alice and Bob. Now greedily it makes sense because the type 1 operation is liked by both Alice and Bob. So I can start with the type 1 operation and I can make them more happy, right? So that wouldn't make my solution go bad. It would actually help me a lot. So initially I'm saying that I utilize the type 1 joke. So when I utilize the type 1 joke, the mood of Alice and Bob actually become equal to A. That is the number of type 1 jokes I had. Also the result or the number of jokes I've already performed is equal to A, right? Now there's a edge case. Now what if my A is equal to 0? In that case, if my A is equal to 0, I cannot perform, I can only deliver one joke at max, right? Because if my A is equal to 0, so the mood of both the people or Alice and Bob, both of them would have a mood 0 itself, right? Now as soon as I deliver a joke of type 2, type 3, type 4, either Bob would get offended or Alice would get offended, or they won't be happy, or neither of the or both of them would get offended or not be happy, right? So in that case, okay, yep, okay, so I think, okay, hmm, okay, cool. So I actually done a mistake over here, but yeah, the constraints were such that it didn't become a mistake. So where I wanted to do a 0, but I had actually written a 1. But great thing that the constraint was set in this way that it's fine. So what would happen is that if my a is equal to 0, then I'll only be able to perform a single joke itself. So in that case, I'll simply write 1 and I'll return. Now, if that's not the case, then I can deliver B and C jokes, or the minimum of B or C jokes, because what would happen is that the type 2 or the type B jokes would make Alice happy but Bob unhappy, and the type C joke or type 3 jokes would make Bob happy but Alice unhappy. So I can only perform the minimum of these two jokes so that both of them don't fall to a value that is less than 0. Cool. So that's what I'm doing over here. I'll be performing the minimum of these jokes, and the result would actually contain double of them, because I'll be performing the whatever the minimum value is amongst these two. I'll be performing that number of jokes from type 2 and type 3 as well. So the like B plus C would get added over here, or 2 into the minimum number would get added over here. Then there's one case. Now let's say the type B jokes are still remaining, right? So if my B is greater than 0, B is greater than C, or B is greater than 0, you can do anything over here. Both actually would mean the same. Then in that case, I can still perform some amount of jokes if if the Bob of or that particular audience or Bob itself has a value or has a mood that is greater than 0, right? So over here I'm checking that the minimum the jokes that I can perform would be minimum of whatever B I am having, or whatever is the mood of Bob, right? In that case, whatever jokes I am able to deliver from type 2, I'll add it to result. I'll decrement Bob's mood by that particular amount, because Bob would actually be unhappy by listening to these jokes. I'll increment Alice's mood by that value, and I'll decrement B, or the number of jokes, by that value of type 2, right? Similarly, I'll be doing the same operation of type C as well. I won't be explaining that, it's exactly the same thing. Then I'll be checking that, okay, so over here what I'm checking is that I still have the type 4 jokes remaining, but type 4 jokes actually tend to offend both Alice and Bob, right? So I don't want to make their values negative, so I can perform only the amount of jokes that is like the least mood available from Alice or Bob. So let's say my Alice had a value of 3 and Bob had a value of 10. Then I can only perform 3 jokes from type 4, because as soon as I perform the fourth joke, Alice would have a mood that it would be negative, right? So that's what I'm doing over here. So then I'll subtract the number of jokes, I'll increment the number of jokes delivered, then I'll decrement the mood of Alice and Bob both, because the type D jokes or the type 4 jokes are not liked by either Alice or Bob. Then I'll increment, okay, over here what you have to see is that what I'm trying to do is that since I want to end my end this particular thing or my show, then I can make the mood of Alice or Bob negative, because in my last joke, if anyone even has a negative mood, then it's fine for me. So over here my minimum now is AL plus 1, or the value of or the mood of Alice plus 1 and Bob plus 1. Also I'll select whatever jokes are remaining with me. So over here it actually is B comma C comma D, so maximum of these, then I'll simply return the result. Cool, that's it for B. This like the only edge case I felt that a lot of people could have done wrong is this one. I don't know why it didn't came to my mind. I actually had 3 wrong answers, and then this came to my mind. Anywho, let's proceed further to problem C. Problem C is not tough. It's a binary search problem, a pretty simple one. So it states that you are given a permutation P of length n, right? And you can perform the operation any number of times. So what we can do is that we can select 2 elements x and y, and then insert the minimum of x and y into the beginning of the permutation, and the maximum of x and y would be added to the end of the permutation, right? In this way we can perform any number of operations we like, and then the final answer or the final permutation we get should be sorted. Now we have to tell the minimum number of operations that can get us a sorted permutation. Cool. So let me try to explain this thing on the iPad. Okay. Yeah. Cool. So let's say this is our array, right? Now interesting thing to observe over here, let's say we are performing x operations in total. Then in the xth operation or in the last operation, no matter what my initial operations were, but in the last operation and also let's say this is a permutation from 1 to m, right? So in my last operation, the two numbers I'm going to select definitely have to be 1 and m itself. Now the reason for that is because the minimum of these would get stored at the first index and the maximum of these would get stored at the last index, right? So only if I have select 1 and m, only then 1 would get at the first index and m would get at the last index. Only then there's a possibility of the array being sorted or the permutation being sorted, right? Also in the second last operation, I have to select 2 comma m minus 1, right? And so on and so forth. I hope you get that idea. So what we can say is that if we are performing x operations, right, then I'm able to manipulate the first x elements and the last x elements. The remaining, that is m minus 2x elements, actually need to be sorted initially, right? Only then I'll be able to do this thing in x operations in total. Cool enough. Now if I'm able to do it in x operations, would I be able to do it in x plus 1 operations? Yes, definitely, because if I'm doing something in x, I can definitely do it in x plus 1, or I can do it in anything in x plus something, right? So this becomes a binary search problem. Now the number of operations can range from 0. 0 would be the number of operations when my entire permutation is already sorted, or they could go up to m divided by 2, where m is the length of the permutation itself, right? Cool, that's it. So that's the entire thing you need to know for this. But how do we check that the elements that are in this particular range, that would be from x to m minus x, they are actually sorted? So for that, what I can do is that I relatively want to check that these elements are sorted. So I can start from my left location, right? I can keep storing the elements I'm observing in a map, let's say. Now once I'm storing the elements in a map, when I come to a particular element, let's say I come to a particular element x plus 1, right? Then I'll check if I've already seen x, right? If I've already seen x, then x is less than x plus 1 and it was also available to its left. So they are technically placed in the right order. Cool. Then I'll also store x plus 1. Then when I'll come to element x plus 2, I'll check if I've already seen x plus 1. If I've seen x plus 1, then well and good. But if I've not seen x and x plus 1, then it means that x plus 1 is somewhere located to my right. Cool. And if that's the scenario, that then the elements from x m plus, okay, from yeah, from x to m minus x are not sorted. So in that case, I can say that this array is not sorted. Cool. So that was the logic required. Now let me take you to the solution. The solution is fairly simple, and it's a pretty small code itself. Cool. So this is a solution over here. This is a binary search boilerplate code. Shouldn't be tough to understand. So the minimum number of operations are 0. The maximum number of operations are r divided by 2 or n divided by 2. Then I'm checking a mid. Then I'm checking if it's possible to convert the array, the permutation, to a sorted state by performing mid operations. If it's possible, I'm updating my result and I'm doing the needful calculations over here. I think you already know about binary search. I'm not going to explain that in detail. Then for the array, I'm checking if the current element is something that is present inside the array that I'm want to check if it's sorted or not. If it's present inside that, and if I've not seen the element, that is just that should have been just left to it. In that case, I'll return 0. Else, I'll just add the element to the set. At the end, if I was able to traverse the entire permutation and all the elements that I wanted sorted were actually sorted, in that case I'll return 1. Cool. So that was the solution for problem C. I hope that helped. Let's move to problem D. Problem D is actually a interesting problem. I think it was kind of easy for the level of problem D, but yeah, it definitely is interesting. So let's get started with problem D also. So problem D states that you are given n permutations. So each of them are actually a permutation a1, a2, a3 up to an. These are not individual elements but individual permutations. So that is something you keep in mind. And each of them are of length m. Then they have given a definition of permutation, and then they are talking of the beauty of a permutation. The beauty of a permutation p1 up to pm be the largest k such that p1 equal to 1, p2 equal to 2, and pk is equal to k, right? So also if p1 is not equal to 1, then definitely the beauty becomes 0 itself. So that's base case, or that's simple to understand. They shouldn't even have mentioned it over here, but cool. The product of two permutations p and q is r such that r of j is equal to q of p of j. So what does this mean? Now let me try to give you an example. Now let's say we're talking of the 0th element, right? So r0 is equal to qp0. So that basically means, now let's say p0 was equal to 3. So that would mean r0, or the element at the 0th location of r, would be whatever element would be at q of p of 0, or q of 3, or the element at the third location of q, right? Then what we have to print is that from each I, from 1 to n, or for each of the permutations, we have to print the beauty of permutation ai into aj, right? So ai we already know, that is the current I, and we can select another permutation from 1 to n, and also I can be equal to j, so we can multiply the same permutation by itself also, and then for that we will be having a beauty. So the beauty is actually defined over here. Cool. And then we have to report the maximum possible beauty. Then they have given us a constraint. So over here one thing interesting to note is that n actually can go up to 5 into 10 to the power 4, but m is actually limited to 10. Now even if we do like come up with a solution that is n into m square, even that would pass, right? So this is an important observation. I hope you are able to understand this. The reason is because n square m or something of that sort is definitely gonna fail, but n m square is going to pass. So we can think of some operations in that manner. Cool. So then they have provided the example for example over here they have given 3 permutations. So these are 3 permutations given, and each of the permutation have 4 digits in them. Cool. Let's try to understand what we can do with it and how we can solve it. So for each permutation, I can actually come up with the required permutation so that my answer is actually m. So let's talk of any of these permutations. So let's talk of 2 4 1 3, right? Cool. So for 2 4 1 3, what would be the required permutation if I want the multiplication of these two to be 1 2 3 4? So permutation 1 2 3 4 would be having a beauty 4, right? So what should that be? So I want that my ri, as they said, should be q of p of j, right? Cool. So r0 should be equal to 1, should be equal to q of p of j, right? That means q of p of j should be equal to 1. I hope that makes sense. Cool. Or over here p of j or p of naught is actually equal to, okay, q p naught equal to 1, but p naught over here is equal to 2, so that means q of 2 should be 1, right? So that would be this. So 2 should be over here. Cool. And then at the second element we have a 4, so that means, okay, so q2 is equal to 1 actually. So okay, cool, sorry. So this should be 1. I'll rewrite this. So this is actually qp naught, right, or q2, this is equal to 1. What about q4? So q4 should be equal to 2, because in the final value we need a 2 over here. Then what about this particular location? So that means qp3 or qp2, like the way you want to say it, 0 base indexing or 1 base indexing. So qp2 should be equal to, okay, qp2 needs to be equal to 2 as well, right? So qp2 or qp1 would be needed to equal to 2 3, sorry. So yeah, 3 needs to come over here, so this should be 3. then finally this should be 4. So yeah, this is the required matrix. So if I multiply these two, then my final answer is going to be this. Cool. So that is something I can do. But now if I want to check that if this kind of a matrix is if this kind of a permutation is available, that's easy to check. But it won't always be the case that the exact permutation would be available. So it might be the case that I have something of this sorts. So let's say 3 1, or let's say, yeah, 4 1 3 2. Now you can check it manually, but I just calculated. So in this case the beauty would have been 2, right? So it is possible that this wasn't available as one of the permutations, but this was available. So how do we do that? Now what we can say is that since my beauty basically means that from I to j, from I to k, pi equal to I, right? So this is basically the beauty. So if my I isn't matching, now let's say if I have 2 1 3 4, right, then my answer is equal to 0, because the first index itself isn't matching. However, if the answer is 1 2 4 3, then my answer at least is 2, right? In this case, although these two indices were at the correct position, still my answer was 0. Over here, these two indexes are at the wrong position, still my answer is 2, because the first element and the second element are at the correct position. So definitely the leftmost element make more sense to me, or the lower elements are more useful for me, because even only if the lowermost elements are available, only then the uppermost elements have a value to add, right? So what I can say is that if this is the matrix required to me, right, over here I said that this is the matrix 3 1 4 2 is required to me, right? Cool enough. So if I have a matrix that is, let's say, anything over here followed by 1, anything over here followed by 2, right? In that case, at least the final answer I'll be getting would be 1 and 2, and my answer would be 2 itself, right? So when I'm saving the values, so if I want to save any permutation, so let that any permutation be this one only, 3 1 4 2. So I'll initially be saving 3 1 4 2 because that's the permutation I have. Then I'll also be saving 3 1 x2. So x is an value over here. Let's say x is equal to -1. That's fine, right? Okay, x is equal to -1, or I can say, cool, or I can say over here. So this is going to be one value over here. So this was the first vector I'm going to store. This is the second value. So this is going to be the third value, -1 1 -1 2. This is going to be the third value. This is going to be the fourth value, -1 1 -1 and then -1, right? And this is going to be the last value, that is -1 -1 -1 -1. So this is a dummy value. Even if you don't store it, it's completely fine. So I hope you got the logic. And when we'll be checking for the availability of permutations that are like me, so then I'll be also performing the same thing. So let's say if this is something you are looking for, 4 1 2 3, then initially I look for this. If this is available, then my answer is 4, right? That's obvious. Now if, let's say, if this isn't available but the permutation available, then I'll be checking for -1 1 2 3. If this is available, then my answer would be 3. Then I'll be checking for the availability for -1 1 2 and -1. If this is available, the answer would be 2. Then I'll check for -1 1. Okay, what messy. Then okay, then a -1, then a -1. If this is available, the answer would be 1, else the answer has to be 0, right? Cool. So this is the solution. I'll try to like go through the code along with you so that it's more easy to explain. So what I'm doing over here is, firstly I'm taking the permutations, and for all the permutation I'm storing that in a set, right? Also, one thing I could have actually done, this is a not good way of storing it, since the values were going up to 10. So I could have made it a long integer and then I could have stored it. So I could have actually done it in a better way. This wouldn't go well with the bigger constraints, definitely. So you should make sure that when it's possible to use the right things, because it was a contest, I was just coding up in a hurry, so I did it in this manner. it's always better if you could actually use an integer and then do the same. Cool. So then what I'm doing is that I'm setting up the values. So okay, so now I want to set up the maximum value as -1, then the second max is -1, and I want to store all of those integers also, right? So in the current, firstly I'm setting the maximum value as -1, right? And then I'm storing it. Then I'm setting the second last value as as -1. Then I'm storing that as well. Then third last value, then fourth last, so on and so forth. I'll be storing all of those values in that available set. Cool. Then for all of those permutations that I have already received, I'll be calculating the required permutation as I suggested. So for the required permutation, I'll be checking. I know that the q of p of I needs to be equal to the number I, right? Over here I'm using zero based indexing, so I have to subtract -1 from here, and I have to add 1 over here. You can actually use one base indexing if you want that, so you don't have to worry about all of this stuff. But anywho, I use zero based indexing. After that, I'll have to check that if the exact required matrix required permutation is present, then the answer simply is m. I can print that, I can continue. But if it's not present, then I'll have to check for the other combinations. So if a matrix from I to or if the permutation from I to m minus 1 is present, I'm not worried about the m, right? And then so on and so forth. So for this, what I'm doing is, in the required matrix, I'll be setting the biggest element first to -1, and then I'll check if that is present. Then the answer would be I minus 1, right? I can print that, I can break it out. If that is even that is not present, then I can set this even the second last element to -1. I can check that. If that's present, good enough. If it's not, I'll still continue. I'll keep on doing this. If I'm not able to find any useful permutation, then in that case my answer would be 0. At the end, I'm simply returning a new line because that's actually required. So yeah, that's it for the solution. I hope you were able to understand it. If you have any doubts, let me know. I'm always more than willing to help you out. Cool guys, thanks for watching this video. Bye bye.